Okay, my name is Rachel Hamilton, and for my senior projects and design project, I did a scaled model of an automatic oyster cage flotation. So oysters need to be flipped into a feeding and desiccation position. This is because underwater oysters are exposed to negative effects of biofouling due to the lack of nutrition. They do need to be in the feeding position though because of the fact that they are filter feeders. They feed off of phytoplankton, algae, and sediment. When they're flipped into the desiccation position, they're able to be removed of moisture. They're able to be removed of moisture from the air and the sun, allowing them to desiccate, eliminating the biofouling. Cage flipping currently is done by hand. As you can see in this picture, it is very labor intensive. It's not a one-person job. Several people need to go out, and due to this being so labor intensive and with several cages, it can be very time consuming in situations of storms where people need to go back out and flip their cages underwater so they are safe. The University of Southern Mississippi has designed a closed system flotation that raises using pumps and lowers using a valve system. The aspiration for this goal was originally for oyster farmers to be able to use this design where they could raise and lower it from a remote location. Now, a closed system means that all of the flotations are closed off except the tubing embedded on the lower portion of the flotation, which I will be showing you in a second. So the closed system shown on the left is completely closed off besides the tubing on the bottom, like I previously mentioned. This tubing allows the float to tilt without releasing any air, so it won't capsize. The tubing does become clogged due to biofouling, which eventually leads to malfunction of the float. The open systems design allows air to escape while tilting, but with the wall in the middle separating the two sections, it still leaves the other flotation intact, full of air, and it'll eventually even itself out, leveraging the air and the water ratio. Now, another important aspect of shaping this flotation was the fact that side floats were definitely needed. A flotation without side floats, as seen from images A through C. In image B, you can see that a destabilizing moment is caused until the top flotation meets the water, seen in image C. And then the side flotations instance on the bottom from images D through F, you can see that the side flotations ensure that the flotation has a stable equilibrium and as the center of buoyancy shifts in the direction of the float. Now, when designing the flotations in Fusion 360, it was important to design the concept with an open bottom, addressing the tubing issue, but also to incorporate the side flotation. So as shown in the lower left corner, you can see that there is the open bottom and the side portion does continue up. The right side is images of the flotation after it was printed. This is the full design at the moment. The CAD model shown on the left was the original design, and it stayed that design over time, except we did end up having to add trusses for stabilization. We found that as the floats were going up and down, they weren't going to be able to stay in the proper position. But the float again uses the pump and valve system. So as seen in this, can you see that? As seen in this engineering drawing, this is where the pump is, and it lets air flow into the flotations. And then when it needs to be released of air, the valves get turned on, and then air slowly leaks out of the valves, lowering it back into the water. Now, the materials used for this were The top floats were made out of water bottles that were electrical taped and also glued with Loctite. The electrical tape was added on the outside to ensure that it stayed airtight during the whole process, as it's not supposed to take on any water. The cage was made out of chicken wire and zip ties. It is a 12 by 12 by 2-inch cage, so the model is a good size to visualize everything. The bottom floats were 3D printed from PETG, Flex Seal, and Loctite. You had to end up spraying Flex Seal onto the 3D printed material because even with a 100% infill density, the material was not waterproof. After sitting in water for a couple of hours, it ended up seeping through, and in the long term, it was not going to work to hold air in it. But the trusses were also printed out of PETG. They did not need to be flex sealed, as it didn't matter if water was flowing in or out of them. Now for the operation, you need to upload code first to the communication board. This allows it to connect to the internet and then read off the controls that it gets from the controller. You can access the controller from cPanel, and at the bottom you can see you can turn the valves and pumps on individually, which is useful if there's any tilting while you're raising or lowering, and eventually you could possibly add a gyroscope to help do this on its own. Now here's the flotation in action. Here's it raising into the desiccation position. I don't know if y'all can hear the pumps on here. Why did it? Giro. It's not.
Yeah, I have to activate computer audio.
Yeah, I'm sorry.
Oh, that's fun.
Now, due to it being in such a small box, of course, the little bubbles after it evened out, showing that it was completely full, did kind of make it shake a little, but in a larger area, it wouldn't have done so. And I was hoping that you guys could hear this, because as the valves turn on to lower it back into the feeding position, they all click, so you can count to make sure that they're all always working. So there are 4 valves and 4 pumps, each connected to each section of the bottom flotations. And it will slowly even out. Oh, it's lagging up there. But now, during my project, I experienced a lot of different challenges, and it was definitely a different learning experience. Some technical knowledge I used was some equations and calculations for figuring out the buoyancy. I used Autodesk Fusion 360, which I hadn't used in a while, so it was interesting getting back into that. And I also used 3D printing that I had never used before, but that was kind of fun to learn. Some of the soft skills I used was conflict resolution, self-confidence, because when I first got into this class, I was afraid to make decisions on my own, and creative thinking. And then a surprise that I encountered was exactly how long 3D printing takes. I 3D printed all my parts over winter break, and the model took over 120 hours, which when getting into it, I was like, it'll be real easy to build. And that was definitely the most time-consuming part besides designing. But In conclusion, the project successfully demonstrated that the open bottom concept does function satisfactorily. The model is stable and it did successfully raise and lower. The new design also addresses the tubing and biofouling issue from the original closed system design done by the University of Southern Mississippi. And if anybody has any questions.